does kinetic mean? And the second is, which of these states of matter do particles move the fastest? Is it solid, liquid, or gas? And then finally, faster particles have blank energy. And then at the very bottom, put a star sticker if you passed your 2E exam that was due yesterday. Now, if you don't know where the star sticker is, it is actually, if you look right here, it is that last picture, and you can find the common symbols, and you can find stars, happy faces, whatever. We just want to see if you want to make your own star. I'm cool with that. I know you, Han, you were kind of saying, I'm going to make my own one. So just go ahead and put that into that bottom box. I'm going to give you only about 30 more seconds to work on this, and then we're going to get started because we have a lot to do today. So 30 seconds up on the clock. Go ahead and get those answers in. Thank you, Natalie. I see your answer up there. Nice job, Gabriella. Emily, nice job. I see your answers up there. Let's see who else is up there. Mrs. Larkin's up there with a star. Good job for passing your test, Mrs. Larkin. And Tyler. All right, so let's go ahead and get started here. So what does kinetic mean? And you're absolutely right. Kinetic means movement, something when we talk about kinetic energy. It's that movement of energy. And so we're going to talk a little bit more about kinetic energy today. And then which of these states of matter do particles move the fastest? Well, if you think about it, you have solid, liquid, or gas. Now, a lot of us said liquid, but think about it. Remember, we were talking about dancing on the dance floor. Solid particles, remember, are just those people that are just going to dance like this right in the center there. Liquid's going to kind of get a little bit bigger, but then gases are going to be the ones that are just going to go flying everywhere. They're just going to be, you know, kind of taking up the whole dance floor. Those are those people that are just, you know, just everywhere on the dance floor. So yeah, it's going to be a gas, absolutely. Now, faster particles move what? More, less, or the same energy? Well, they move more, okay? Obviously, when we're talking about faster particles, they're moving around everywhere. Think of our states of matter, the gases, how those particles are moving faster and faster. So, absolutely right. Good job, everybody. They are moving more. So, very amazing stars. I love them. They look like, oh my gosh, who's putting the little, it looks like Mario stars on there. That's classic. My son would love looking at those little Mario stars. That's funny. So, with that being said, nice job, everybody, with the 2E exam. If you haven't gotten that 2E exam, we have an hour after class, so you can get that extra credit. So, make sure you get that in so you can have all the potential of getting a good grade. All right, so with that being said, I'm going to go ahead and start our recording here. Should have started a little earlier.
Recording started.
So remember, Class Connect sessions are recorded and distributed for learning purposes. Please do not put any personal information or the information of others into the chat box for your protection and the protection of others. All right, with that being said, we're going to go ahead and look at our schedule here. Now, hopefully you got your announcements video. You watched it for this week. That we're going to kind of cut down our announcements so we can get through more of the material, and it's not so fast, and we can take our time with the material. So you're probably going to be getting a weekly announcement video just so that we can cut down on that, all those announcements. Plus, it's more information we can tell you all. With that being said, today is the 10th day of our 45-day quarter. It is April 28th. Welcome in, and we're going to be talking about gas properties. We have class until about 2:45 so that we can have time for those who need questions being answered or if you need to go back on your notes. With that being said, today we are going to be working on our 3A notes, and then obviously doing that extra credit, okay? Yesterday you were to do that 2E exam. You were, if you needed help during class, we were here for you. It was kind of like a support session, but you were able to do it more independently. A lot of questions have been given up, a lot of questions about the video and about the recording. A lot of you were confused about the dates. We took that, those videos, those clippets from those videos for that particular question so that you could review it. We've already talked about it, so if you've been in class and you've been participating, then this should have been pretty easy. So it wasn't one big video recording for you. It was kind of little snippets of the past recordings, okay? All right, so with that being said, we're going to go move right on into Unit 3, gas laws. We're going to talk about how the environment is made up of gases. When we think about it, we're breathing in gases. Every time we walk, we're walking through a big gas. Students examine the laws that govern gases, and we pay particular attention to the effects of pressure, temperature, and volume. Okay, and obviously we're going to demonstrate this through our laboratory, and we're going to actually have a lab. I believe that it's on Thursday. So, and if I'm wrong, Mrs. Larkin, please in the chat box let them know. But I think it is on Thursday. No worries, Jaden. No worries. All right, so let's look at our objectives and our agenda. Today we're going to talk about physical properties of gas. We're going to explain the kinetic theory of matter, and it accounts to the behaviors of gas. So we're going to kind of connect those together. We're going to talk about examples of how pressure, temperature, volume, and quantity of gas are related. And obviously we're going to demonstrate that through your 3A notes with 100%. So those, the links for those notes have been going up in the chat box periodically. So make sure that you click on those links. Again, if those links don't work, you can always find your notes in your grades tab. So this is our agenda for today. So if you have any questions, please let us know in the chat box. All right, with that being said, I would like you to go ahead and open up your notes and click Start. Important, you can also make sure that you are ready for your pictures or screenshots. If your computer does not like two things open at one time, you're more than welcome to do those pictures and screenshots. With that being said, please give me a green check when you have your notes ready and open to go for 3A. Green checks, everybody. I'm going to give you about another 20 more seconds. They're also posted right up on the board here. And if you are watching the recording, in order to find your notes, you're going to click the Content tab, Unit 3, scroll down, and find your 3A notes and start your quiz. You can also find it in your Grades tab. Excellent. There are 44 of us in class. I have 26 green checks. Alicia, Alvin, I need to see a green check. Alyssa, green check. Connor, green check, thank you. Diego, green check. Jade, green check. Again, those links are going right up into the chat box. Mike, green check. Joel, green check, please. Carla, green check, excellent. Lillian, green check. I still see 34. I need to see a lot more green checks in order to move on, folks. Again, yeah, good job. Excellent. All right, here we go. Now remember, your notes are provided word for word, so you could get a perfect score on this, so make sure you are paying attention. So let's look at this mind map here. Intro to gases. We know that a gas here could be fluids. It is in our Earth's atmosphere. It is composed in our Earth's atmosphere, and it's described by the kinetic theory. We're going to talk a little bit more. Mrs. Lark is going to talk a little bit more about how it's being described through the kinetic theory. As we look at here how it's composed in the Earth's atmosphere, again, it's all around us. It creates air pressure. We have air pressure in order for us to breathe. And so we breathe in gas, we breathe in oxygen, and we breathe out carbon dioxide. And obviously plants interchange that with that, by taking in the carbon dioxide and breathing out that oxygen for us to breathe. So again, it is created in the air pressure we have in our world around us. All right, I'm going to turn.
All right, looking good. I think you should be able to hear me now. Perfect. Okay, so let's go ahead and do a quick brainstorm in the chat box or on the whiteboard. I'll give you some tools as well. Tell me, what are some things that you can do in order to open up a locked door quickly, like you might see in TV? What do people often do in order to get that door open? How could you make it easier? Yes, I see Zashiki's got something in the chat box. I see Jay's working there. Yes, I'll go ahead and put some of these up on the board. Board. Good. Yes, we could unlock it, but what if it is locked and we don't have the key? Awesome. Pick the lock. Cool. Punching. Oh my goodness. One punch man over here. Use a car. That's one I've never heard of, but that would probably work, right? Shoot the doorknob. Chainsaw. I don't know. Do you all have just have chainsaws in your pockets? A helicopter? All right. I think you guys are getting a little bit silly here. Awesome. So the one that I do see the most frequently is definitely kicking it. Now, when we want to kick the door, all right, one thing that I've noticed is that sometimes if it's a really big door, you can actually have two people kick the door down. And do you think, is that going to be easier or harder? Tell me in the chat box. If it's just you kicking it versus you and a friend kicking it, is that going to be easier or harder to get the door open? Why would it be harder to get the door open? I would say easier. But let me know in the chat box if you think it's easier or harder and why. Getting some answers in there. Oh, sorry. Okay, I should say like wider, but still the same weight. So the doors are the same strength, and so if you add another person, is it going to be easier or harder? If you have two doors, they're the same strength. One of them you're trying to open by yourself, the other one you have a friend, and the doors themselves are the same strength, then is it easier or harder by yourself or with a friend? Yeah, it's going to be easier, and the reason it's easier is because you have someone else to help you to try to hit that door to get it open, right? Go ahead, give me a smiley face if that makes sense. I see where we got confused. But yeah, go ahead, give me a smiley face if that makes sense. Awesome. Now the next question is, if you don't kick it down the first time you try, what do? Do you just give up? Do you walk away? And we see this quite often in TV shows as well. More comedy shows, I feel like. No, you keep kicking it. Awesome. Okay, so here's what I'm saying. When we want to open a door, we need to keep on hitting it, right? So either we hit it harder, so maybe you take a running leap towards the door, maybe you get a friend to kick the door with you, or you hit it several times, kind of weaken it, get it to go down. Even if you're just using your shoulder or a sledgehammer, all of those things are true, regardless of what body part or object you're using to open it up. I think all those things are true. If you use more force, if you hit it more times, if you, let's see, you would walk away. Awesome. Yeah, if you use a door jam, like maybe cops use. Excellent. Okay, now as we're thinking of these things, we're going to actually relate this to gases today because gases actually do a lot of the same things. So if you imagine containers are like the door that you're trying to get through, gases are oftentimes doing the exact same things. So let's go ahead and take a look at that today. So some quick review that we already know about gases is, remember, gases have a lot of thermal energy. We went over this during our brain stretch. We made a couple mistakes, so I do want to make sure that we really know this, but they have high thermal energy. Think about how chaotic steam is compared to liquids. Liquids stay in the pot, steam goes everywhere. So gas particles have a lot of energy. They're sprinting around, they're chaotic, they move randomly, they try to expand and spread out. But the result is, because they're moving so chaotically, they're going to collide with each other, and they're also going to collide with the walls of their container if they are in a container. Yeah, you could throw something heavy at the door, a battering ram, exactly. So all of those things, I promise, will relate back over to gases in just a moment. Now, again, gases, because they have all of this energy and they can escape and expand, they will try to take up their entire container, assuming they're in a container. If they're not in a container, they'll try to spread out indefinitely, which means forever. And the result is they also have no fixed shape and no fixed volume. They can spread out to take up as much space as they want, and they can also change their shape, a lot like you see smoke changing its shape. All right, so this should all be reviewed from last unit. Again, we are in a new unit now, but this should be pretty familiar. Go ahead and give me a music note if you feel comfortable with these properties of gases, because this is going to kind of set the foundation for the rest of today. Perfect. Okay. So again, lots of energy, moving really fast. Now, remember, also relating back to a previous unit, we talked about the kinetic theory of matter, and during our brain stretch, we remembered that kinetic means motion. So we talked about kinetic theory of matter, which is that all particles are moving. Now, gases specifically, those particles have a lot of energy. They're moving, they're colliding, they're running into each other, they're running into the walls of their container. A lot of times what I like to think about is I like to think about gas particles as people that are in a room, and the faster those people are in a room and sprinting around, do you think that there's going to be more bumps and bruises or less bumps and bruises? Do you think people are going to collide more or less if we're all in a room and we're sprinting around? Yeah, definitely more collisions. Now, what we're going to learn today is that collisions is another word for pressure when we're talking about gases. The more collisions there are, the more pressure there is. And that relates right back to our brainstorm, where the more you're colliding, the harder you're colliding with that door, the more pressure you're putting on that door, and the more likely it is to open. Go ahead and give me a lightning bolt if that's beginning to make sense. The more you collide with the door, the more you have friends colliding with the door, the harder you collide with the door, the more pressure there is on the door to open it up. Same thing with gases. You can see our picture over here where we have a lot of people in a small space. This is going to be a high pressure area. There's going to be a lot of collisions if you imagine these are like gases. And you can see a better picture down here of actual gas molecules being represented, that these ones on the right are going to be colliding a lot more. They're all squished together. They're going to run together, or they're going to run into each other, and you're going to end up with a lot of collisions, a lot of pressure. Okay? Now, let's go ahead and relate this to a real life scenario, which is the Earth. So the air that you're breathing in, a lot of us think that, oh, we're breathing in oxygen, which is true, but most of the air you're breathing in is air that you don't actually use, and that is nitrogen. So 78% of the air that you're currently breathing in is nitrogen in the form of N2, two nitrogens bonded together, and only 20% of the air you're breathing in is actually oxygen. Okay, so 20% of the air that you're breathing is oxygen, O2, two O's bonded together. And then there's a little bit of other stuff, right? So 1% argon, there's a little bit of CO2, obviously, that we're breathing out, that cows are farting out. So lots of different gases in our atmosphere. Okay, now one of the things that I want you to think about is when you climb up a mountain and you get higher and higher and higher, does it get easier to breathe or harder to breathe? That is actually where a lot of CO2 is contributed to our environment, is from cow farts. It gets harder to breathe. And why does it get harder to breathe the higher up you are? Tell me in the chat box, why does it get harder to breathe the higher up that you are? Yeah, there's actually less oxygen higher up in the atmosphere. The air is thinner, and what's also happening is there's actually lower air pressure the higher up you go. Now, this has to do with a concept I think you're familiar with. Do you guys know what this is called down here? What's going on with these baseball players right here? What is that called? Yes, less oxygen up there. Yeah, this is a dog pile. Huddling, I think, would be much nicer. These people are actually jumping on top of each other. So this is a dog pile. And what I want you to think about is, who would you rather be? Would you rather be the person on the bottom of the dog pile or on the top of the dog pile, and why? Tell me in the chat box. All right, I'm saying most people would rather be on the top of the pile. And why would that be? Yeah, the person on the bottom can't breathe, right? You don't want to get squished by all these people. So this is actually exactly the same thing that's happening with air particles. Air above you is a dog pile, which means that the more particles there are above you, the more those ones on the bottom are being squished, and the higher pressure there is, and the more particles there are there for you to breathe. Okay, just like you can see over here. All right, go ahead and give me a thumbs up if that's beginning to make sense. So the lower you are, the more pressure, because of all the particles above you that you have, squishing you closer together, making the air more breathable. All right. Now, taking a look here. So air pressure is going to actually decrease as altitude increases. Altitude meaning your height. So the higher up you go, the less air pressure there actually is. Let's go ahead and take a look at an example here. I'm going to go ahead and pause this video. All right, so you can see here that below that like level 4 of the atmosphere, is there a lot of pressure or a low pressure down there? The pressure on the right, that shows you pressure, 100, 200. At the bottom, below level 4, is there a little pressure? Yes, there's tons of particles right there. They're squishing each other down. They're dogpiling on top of each other. Awesome. Now closer above 8, are there a lot of particles above 8? Are there a lot of particles above 8? No, and so there's less people. These are like the people on top of the dog pile, and so you're not feeling as much pressure, but at the same time, you're not being squished together, so there's not as much air for you to breathe. Go ahead and give me a rainbow if this GIF makes it make a little bit more sense. All right, now that you're actually seeing it in action. Perfect. All right, cool. So let's go ahead and jump back over here, and let's make sure we really understand the properties of gases.
Let's go ahead and look at our check for understanding. Number one, I'm going to go ahead and switch your polling tools to A, B, and C. D, there you go. So which of these statements is false about gases? Use your polling tools. Is it A, they take the shape of their entire container? Is it B, they have indefinite shape and indefinite volume? Is it C, more particles collisions result in less pressure? Or D, air pressure decreases as altitude increases? Remember, we're looking for false. What is the false statement about gases? I'm going to give you about 20 more seconds to go ahead and lock your answers in. 20 seconds up on the board. I just put 2. I apologize. I was meaning to put 20. Get your answers locked in. I still need to see an answer from Alvin, Alyssa. Angelina, answer please. Anne Marie, April, answer please. Brittany, answer. Connor, answer. Or CJ, I'm sorry. Lock in your answers. Emily, Enrica, answer. Excellent. Nice job. So let's go ahead and post your polling. All right, so majority of us said C, and that is correct. C is correct. Right there, you're going to need more particles collisions results in more pressure. We just saw that demonstration that Mrs. Larkin did, so when you notice that the more they're colliding together, the more pressure that they're building. So absolutely, C is correct. More particle collisions result in more pressure. So this one is false. So when I say correct, this one is the false statement, okay? All right, so let's go ahead and continue on. So let's look at this mind map here. Oh, I apologize. Thank you, Mrs. Larkin. This is question number 1. I apologize. Go ahead and lock in your answers. I'll give you 30 seconds to lock in your answers for number 1. Make sure you read those answers carefully so that you can get it into your notes. Give me a green check when you have finished number 1. 10 more seconds. And I have 33 green checks, and I have 52 of us in class. So I need to see a little more green checks on there. Alvin, Alyssa, green check. Brittany, green check. Cody, CJ, green check. Enrica, green check. Ethan, green check, please. Joel, green check. Carla, green check, please. All right, Raphael, Rosemary, green check, or Rosario, green check. Thank you so much. I see that. Samantha, green check. Excellent. Thank you, everybody. All right, so let's go ahead and now go to this mind map of gas properties. We're talking about gases here, and so we know that gases have some physical properties. They have a temperature, which affects their volume. They also have volume, and they also have pressure that affects volume. And so we're going to go ahead and talk a little bit more about how these physical properties affect gas.
All right, looking good. All right, I think you can hear me. Perfect. All right, Kate. So I am going to go ahead and I am going to show you a really fun video. Not really. It's actually a little bit scary, but it's pretty amazing how this happens. I'm going to go ahead and show you a video, and I want you to give me a green check when you finish watching it. I'll put the direct link in the chat box if it does not work for you on the screen for some reason. So again, direct link will be in the chat box. So here's that direct link, and I'm going to go ahead, and what you should be thinking about is, why did this explosion happen? Let's go ahead and take a look.
And now to a CBS 4 News safety alert. A Missouri mother is warning people not to leave aerosol cans in hot cars. That's after one exploded in her daughter's car, damaging the sunroof and leaving broken glass everywhere. Mother Christine Deberick says when her husband first noticed the damage to their daughter's car, they couldn't figure out what happened.
We were all just shocked. We had no idea what happened. We thought maybe something fell from the sky or something like that.
And when they got a look inside, they were still without answers.
It looked like a tornado hit the inside of the car.
Green checks if you finish watching that. I know. Oh, please make sure you use appropriate language, Laura. But let me know in the chat box, what do you think happened? Why did that happen? Yes. All right, so we saw that there was a bottle of dry shampoo which has some gas in it, right? It's an aerosol can, so it has some gas in it. And so the pressure began to build up because it got too hot and then it exploded. Now, they didn't get an actual video of it exploding, but you did see the after effects. So I would say make sure don't leave aerosol cans in your cars on hot days because you could yourself get hurt as well as your car could obviously suffer a lot of damage too. Cool, so let's go ahead and talk a little bit. We kind of know why this happened, but let's go ahead and talk about what's actually going on in the background, like scientifically why this happens. Okay, so that being said, gases have three properties that we're going to be taking a look at in depth this unit. So the first one, yeah, it could definitely hurt you really bad. Yes, I would not want to be in that car. There are three things we're going to be taking a look at in depth. We're going to be taking a look at pressure, which we talked a little bit about already. We're going to take a look at temperature, which we kind of know about from last unit, and then we'll also be taking a look at volume. Now, all of these properties are related, and if you change one property, it actually affects all the other properties as well. Now, what's important to remember is I'm calling these physical properties. Remind me again, if these are physical properties, then does changing one of these properties change the identity of the gas? Does the gas itself change its identity if you change the pressure, temperature, or volume? No. They're only physical properties. So you can change the pressure, you can change the temperature, you can heat it up, you can squish it together, and it would still be the same gas. All right, go ahead and give me a bat if that makes sense. This is something we learned from the first unit. This is a physical change. It's not going to be a chemical change. It's still chemically the same. Awesome. So let's go ahead and take a look at these properties. The first one, again, we talked a little bit about this already, but just the formal definition is pressure is the force of a gas pushing on its container walls due to particles colliding. All right. So again, yes, she just woke up from her nap. She might say hi later. She just wants to hug me right now. All right, so pressure is the force of a gas pushing on its container walls due to those collisions. So we kind of talked about that already, but again, it's a lot like our door. The more you hit the door, the more likely it is to be broken down because of the force that you're putting on it. Okay, now in our class, we'll generally be measuring this in kilopascals, but you can actually see there are many different types of units we can measure this in. Just like you can measure distances in meters and feet and inches, you can also measure pressure in a lot of different ways. And an example would be like a mountain bike tire needs 300 kilopascals of air on average, of pressure on average in order to operate well. And you can kind of see a gauge right here. How many of you have ever filled up a tire? Tell me in the chat box, how many of you have ever filled up a tire? Yes, awesome. Okay, yes, a bike tire. Exactly. All of those things are going to require a certain amount of pressure to make sure they operate correctly. Awesome. Now, temperature, on the other hand, we talked a little bit about already. Temperature is how hot or cold something is, right? So we took a look at some different scales. We talked about how we use Celsius pretty often in class. Fahrenheit is what we use in our country. And we also learned about the Kelvin scale, where 0 is absolute 0 on the Kelvin scale, which is as cold as things theoretically could ever get with no motion. But temperature, again, is how hot or cold, but the scientific definition is it's the average kinetic energy of the particles. Because remember, heat is energy. So the average motional energy of the particles, that's going to be your overall temperature. Go ahead and give me a birthday cake with some candles if that's beginning to make sense. Birthday cake if that's beginning to make sense. All right, we kind of know what temperature is, but again, I want you to relate it to motion now. It's related to kinetic energy. Cool. Now, as we increase temperature, we're going to actually get more energetic particles because we know temperature is related to motion. So we get more energy, and if you have a lot more energy, again, think about our people trapped in a room. If they get more energy, they're sprinting around, what happens to our collisions? What happens to our collisions? Yeah, there's going to be more collisions. You're definitely going to collide with each other more. And so that means your pressure will be increasing because collisions is pressure. Let me go ahead and show you a great example of this. So I'm going to grab our FET right here. And again, I'll send you this link because I always love playing with these. And I'm sure some of you enjoy them too. So there's the link to that. I'm going to go ahead and share it with you up on the board now, so you can follow along if you would like on your own. We're under the ideal part. So go ahead, open that up if you want, and then click on the ideal part of the lab. Cool. All right, so I'm going to go ahead. I am going to add some of the smaller particles just because I like how they move faster. All right, so we got a bunch of particles. There we go. Add as much as you want. Perfect. Okay, so we have a bunch of particles here. You can see that right now it's about 300 Kelvin, so 27 degrees Celsius. That's about room temperature. All right, let's go ahead and heat it up though, and tell me, what do you see happening to these particles as they get hotter and hotter? What do you notice is happening to the speed of the particles? Yes, they're moving faster and faster. Again, if you're opening it up on your own, you might see that a little bit better yourself. But yes, they're getting faster and faster. And now what I want you to notice is watch this temperature gauge, this pressure gauge, as I continue to add higher and higher temperatures. What's happening to the pressure? As it gets hotter and hotter, what's happening to pressure? Yes, they move more and more and more, faster, faster, faster. And therefore, what's happening to pressure, to collisions? Yes, it's increasing. You can see that it's moving upwards. You can see that this gauge is increasing until at some point it gets so hot that what happens to our container? Just like our car and bottle of shampoo. It explodes. It goes boom. Exactly. And those gases escape. Perfect. Okay, so again, a lot like our door where we are knocking down this door. Cool, this is number 2 in your notes. Go ahead and fill in the blank with the word collisions and only the word collisions. Make sure you spell it correctly. 2 L's. Green checks when you have that saved. You have 30 seconds. Go, go, go. Okay, just waiting on a few more green checks. Elvin, Alyssa, Angelo, waiting on Brittany, Cody, CJ. Green checks, Emily, Erica, Ethan, Gabby, and Kika, Joel, Yuhan. Let's see here. Green checks, Kayla, Sam, Chanel, Tristan. There we go. Awesome. So cool. All right, so the second to last relationship we want to take a look at is pressure and volume. So again, we talked about pressure being collisions already, but now we're going to relate it to volume. So volume is the space that a gas will take up. And remember, gases are going to expand to the size of their container, so whatever the container's volume is, that is also the container of the gas. Go ahead and please give me a... Give me an 8 ball if you understand. All right, since gases take up the entire container, whatever the container looks like, that's what the gas looks like. Cool. Now, here's the problem though. If you change the size of the container, then that's going to actually change the pressure, because that means that now the gas's volume changes, and we've talked about how these things interact and affect each other. Okay, so let's go ahead and talk about an example here of Harry Potter in Hogwarts and Harry Potter in the cupboard under the stairs. Okay. So I don't know if you're a Harry Potter fan. I definitely am. But let's imagine Harry's got his what, 6-ish friends. I mean, you throw Luna in there. All right, so let's imagine we've got Harry Potter and his, well, let's say a total of 6. So a total of Harry Potter, 5 other people, that's a total of 6 friends, okay? Now, if we were to take those 6 friends and stick them all into his cupboard, okay, so let me go ahead and draw this in here. Oops, sorry, my daughter is climbing on my arms. Let me go ahead and put them in here. All right, so we've got 1, 2, 3, 4, 5, 6. What do you think? Are people going to be colliding into each other a lot? If we stick all 6 of them into the cupboard, lots of collisions, little collisions, what do you think? Tons of collisions. You're going to have elbows in your face the entire time, right? So we end up with a lot of collisions. So many collisions. So this is a small volume, right? So a small space. And so we end up with many collisions. And collisions is what? We've talked about this several times now. Collisions is what? Collisions is pressure. So many collisions means lots of pressure. Lots of pressure. Here, let's see if I can maybe change the colors of these a bit better. I don't know. All right, perfect. Now, on the other hand, let's take those 6 friends, same 6 friends, and let's go ahead and put them into Hogwarts. So I'm going to go ahead, put them into Hogwarts, and now tell me if they have all this space to move around. So we've got a big volume now, but still only 6 friends. Are they going to have lots of collisions or fewer collisions? More collisions or less collisions? Yeah, they're going to have a lot fewer collisions because now they have all this space. So this one is kind of opposite. So previously we saw that the hotter things get, increasing temperature, increasing pressure, it goes boom. But when we actually increase the space or the volume, the opposite thing happens because again, it has to do with collisions. So the more volume or space means that there's actually less collisions. And if there's less collisions, there's also less what? More space for those particles to move around, less collisions, and therefore, yes, Gabby's got it. Less collisions, less pressure. Perfect. Okay, so you can see a picture of that over here as well, right? So these ones are going to collide less in the bigger space, collide more in the smaller space. Go ahead and give me a house if you understand. House if you understand. Looking good. This is number 3 in your notes. Please fill in the blank with the word decrease and only the word decrease. You have 30 seconds. Go, go, go. Looking good. All right, I don't know. I don't remember if I cleared out the old green checks actually. Green checks, let's see here. Mafi and Joel, Jade, green checks, Erica, Ethan, CJ, Brittany. I did not. That's okay. No biggies. Green checks, let me know if you need any more time. Looking good. All right, here we go. All right, so that's good, Jackson. All right, so the last one we're going to talk about is how quantity is related to pressure. So when we increase the quantity, or the amount of gas particles, that's also going to affect the gas, okay? Now it's going to affect it in a couple different ways. It kind of depends. Oh, honey, I need those balloons, please. I need the balloons to show my students. Thank you. I can go back to it, Dakota. I don't remember. All right, so here's the deal. Now, if we have a volume that is fixed like a scuba tank and I'm adding more and more and more gas into that scuba tank, what do you think is going to happen to that scuba tank? If I'm just trying to get more and more air into it, what do you think is going to happen? Tell me in the chat box. Yeah, eventually I'm going to add too much and it's just going to blow up, all right? Now, for a while, it'll be fine because scuba tanks are really strong. So for a while, it's going to increase pressure and the gas will stay in there and it'll be fine and the gas will be it'll be what's called compressed, right? But you guys are absolutely right. Let me go ahead and show this to you really fast on the board. You're absolutely right, though, that if we keep on adding too much, then we have a problem, right? So let me go ahead and redo this one. Here we go. So if I'm just consistently adding more and more particles, eventually the pressure is going to be too much, right? You can see the pressure gauge increasing. And the scuba tank right now, this is all compressed gas, all right? So there's a lot of gas in this scuba tank, but the more and more I add, the more pressure there's going to be. Actually, I don't think it's letting me add more. Hold on, let's see if we can add more of the heavy ones. Here we go. There we go. We'll add more particles of the other one. It doesn't even want me to make it explode. It's like too much, Brittany. There you go. And you can see it explode, okay? However, on the other hand, there's a different scenario where if the volume of the object can change, then this changes what's affected. So this is a scuba tank versus a balloon. Now, when you add more to a balloon or to a tire, it actually blows it up. So that means it's actually increasing the volume of the object. Go ahead and give me a smiley face if that's beginning to make sense. So if it's fixed, it increases pressure until it explodes, okay? If it's not fixed and can change, then it's just going to get bigger to accommodate all those extra particles. So here's an example that I have. All right, I have a balloon that my daughter keeps on trying to steal from me. All right, so again, let's imagine I add a little bit at a time, right? Continue to add more. And you can see that as I add more and more particles, this balloon gets larger and larger, right? So it's just accommodating all that extra stuff without changing the pressure. If the pressure changed too much, then my balloon would explode, right? I know. All right, go ahead and fill in the blank with the word compressed and only the word compressed. Again, that's what happens when we have a scuba tank. All right. Green checks. Give you another 20 seconds. Mental 20 seconds since my hands are full and I didn't put a timer up. This is number 4. Make sure you spell it correctly. It's got 2 S's. And here's my little virtual gift to you today. All right, looking good. All right, that's number 4. Still waiting on some green checks from Elvin and Alyssa. Thank you for the applause, Andrea. Waiting on Brittany and CJ. Green checks, please. Diego, Dominic, Asia, Erica, Ethan, Hunter, Ileana, Jade. Green checks, please. Kika, Joel, Yuhan, Jay, Mafi, Noah, and Tyler. Awesome, looking good. We did answer number 1, Kayla, so if you missed it, we can go back to it after class. Cool?
Alrighty, well, I am not as cool as Mrs. Larkin. I do not have any balloon tricks for you today. I am not handy with the balloons or anything like that, but let's go ahead and check our understanding right here. So I want you to take your whiteboard tools. I'm going to turn them on for you. I want you to match the term pressure, volume, and temperature with the definition. I'm going to give you about 30 seconds to do that. So go ahead and get started. You are doing awesome, everybody. Thank you so much. Awesome possum. We just have about 1 more second. Here we go. So we're going to go ahead and go through this. It looks like everybody got it correct. So I'm going to clear the page up so I can go through it. So here we go. Pressure. We know that when we talk about pressure, we're talking about the force a container, or the force that on a container's wall from a gas particle's collision. So we know that when, we talked about different things, the scuba tank, the pressure on it and how it builds, and we talked about how, the more pressure it eventually can't get out, that gas can't get out and will explode. The volume is the amount of space that gas takes up. Now, it can change volumes, obviously. If I had a cup of, if I had volume of a big cup, and then I put the volume into, and then I put gas into a large cup. We already know, just like the Harry Potter example, that you can't stick all of Harry Potter's friends in that cupboard underneath the stairs. They're not going to be able to move. They won't be able to sit. But you could stick Harry Potter's friends all in Hogwarts, and there'd be a big old space for them to move around in. Temperature is the average kinetic energy, hot or cold, of gas particles. Okay, so here is number 5. I'm going to give you about 30 seconds to get that into your notes. Now remember, these are scrambled, so take your time. When you are finished, green checks all around, and we will then continue on. Alrighty, so hopefully everybody got that in. I still see 32 green checks. I know there is 52 of us in class, so let's get those green checks in as I scroll down. I need to see a green check from Alyssa. Green check, please. And April, green check, please. Brittany. Kiko, green check. CJ, green check. Daniel, green check. I see a lot of good participation out there. Dominic, green check. Excellent job. Enrique, Ethan, green check. Joel, Yuhan, green check. Jay, green check. Mafi, green check. Excellent job, everybody. Here we go. So with that being said, we have kind of covered everything that we're going to be talking about today. So today we obviously talked about the physical properties of gas. We talked about how kinetic matter theory of matter is connected to the behavior of gas. We provided examples for pressure, temperature, volume, and quantity of gas and how they are all related, and we did this all by demonstrating that in our 3A notes. Now, I know everybody got 100% on those notes, so right now I'm going to go ahead and do just a little reflection of how much do we understand our objective today? How much do we understand what we talked about with gases, particles, and pressure, and how they all relate together. So I'm going to give you your whiteboard tools. Give me, are you in awesome? Are you feeling pretty good? Still need some help, or very confused? Go ahead and use your whiteboard tools to let me know how you are feeling about today's lesson. Woo! Everybody looks like you are doing excellent. Nice job. I am so happy to see that everybody is feeling pretty awesome. All right, so right now, what I would like you to do is submit that, click that submit button right there and complete your 3A notes, because once you complete your 3A notes, and I know since everybody got 100% on those notes, that you are now able to Ta-da! Get your extra credit attendance. So right now, we will go back, Hunter. Don't worry. At the end of class, if you get your extra credit attendance, and we're gonna go ahead and put that up on the board or in the chat box there. And give me just a quick second. There you go. The extra credit word is air. Now make sure you spell it correctly. E-Y-R-E. Air is our extra credit word for today. Now remember, you have until 4 o'clock tomorrow, to get that in.
Recording stopped.
With that being said, if you are all set, then you are free to head out. If you have any questions, by all means, stick around. I know, Hunter, you had a question about number 1. We will go back to that. You